Hi, welcome to Chapter 5, Overview Part 3, where we're going to continue talking about calorimetry. Focus a little bit on how to do calculations with that. So there are various types of calorimeter problems, and I wanted to break them down for you so you can understand it. So there's mainly 4 types. One where you're finding the specific heat of a pure substance, okay? And that could be really simple where they just say you heat the substance and you can calculate Q from that. But if you're using it in a calorimeter and the water in the calorimeter is absorbing the heat, then you need to use Q of the surrounding equals negative Q of the system. So that's only if there is a system and a surrounding mentioned it, okay? The second type is when you're making a solution or a dissolving process, okay? So you're dissolving, let's say, an ionic salt in water, and you want to measure the heat that is produced from that reaction. In this case, again, you'll probably have to use Q of the surroundings equals minus Q of the system. But you will also, and this is kind of important here, you will also have to add the mass of the solute plus the solvent. And that would be your M in Q equals MC delta T. So this M here is the sum of the solute and the solvent. The third type is when you're mixing 2 solutions, 2 aqueous solutions, and you want to get the heat of the reaction. The heat of the reaction is going to actually be equal to negative the heat of the solution. So again, you're measuring it's in a calorimeter, and you're measuring the change in temperature of the water. And what you have to do is you have to add the volumes of each solution together, and then you assume that the solution has the same density as water, which is 1 gram per milliliter. So then you can take the volume and convert it to grams, and that would be your mass. And the last type is how do you calibrate a calorimeter? So let's do an example here. We're going to start off simple and then work our way up, where we want to calculate the energy needed to change the temperature of 50 grams of aluminum from 20 degrees to 30 degrees. And they give us the specific heat is 90. So the first thing you should always do is list your information. So your specific heat is C, and it's 0.90 joules per gram degrees Celsius. Q is what we're looking for because it's calculate the energy. Okay, that's Q. M is our mass, and our change in temperature is always the final temperature minus the initial temperature. So that would be 10 in this case. You plug everything in, and here is your answer. What that means is you would use 450 joules of energy to heat 50 grams of aluminum and have its temperature raised by 10 degrees. Now, what if you use the same amount of energy, but instead of aluminum, iron is your metal instead of aluminum? Would the temperature change be the same, less, or greater? So what you need to look up is what is the specific heat of iron, and it's 0.45 joules per gram degrees C. Okay, so it is about half of what it is for aluminum. So what you do now is you kind of solve this equation for delta T. Okay? And you can plug in the numbers if you want. 450 divided by 50 divided by 0.45. And when you do that, you get a change in temperature of 20. So the temperature change would be greater. And let's think about this. The heat capacity is smaller, so it has less ability to store heat. So all that heat is going into changing the temperature. So the lower C, the greater the temperature change. If you're keeping your mass and energy constant. Okay, so now let's look at this problem. Here, a student heats up a 5-gram sample of an unknown metal, so there's your mass, to a temperature of 207, and then drops this into a coffee cup calorimeter. So that's your styrofoam cup calorimeter that we talked about last time. And in the calorimeter, you have 36 grams of water that's at 25 degrees C. Then you wait until the temperature reaches an equilibrium. And the equilibrium temperature here, or the final temperature, is 26.0 degrees Celsius. What is the specific heat of the unknown metal? And they're telling us the specific heat of water is 4.18. And we're assuming that all the heat from the metal transfers directly to the water, nothing is lost. So here we have a system and a surroundings, okay? Our system is the metal. So our system is the metal. Our surroundings is the water. And remember, Q of the surroundings is equal to negative Q of the system. Or if you want to put in water and metal, Q of the water will equal negative Q of the metal. So let's look at our water first. So here's the mass of our water. Here is our C for water. Here is the change in temperature of our water. And that produces 151 joules. Okay? This should be a lowercase q. Sometimes PowerPoint autocorrects those things. So if Q of the water is 151, it absorbed that much heat, then the metal lost 151 joules. So our Q of the metal is negative. We plug in all of our things and then solve for C. And we get, this is C of the metal. And then normally you'd have like a data table. You could look it up and see what metal it is. What if we are dissolving? Okay, so here they're telling us the molar heat of a solution when you're dissolving sodium hydroxide is negative 445.1 kilojoules per mole. And you're dissolving 5 grams of sodium hydroxide in 1 liter, and it is originally at 20 degrees C in a foam cup calorimeter, same thing as a coffee cup calorimeter. You're assuming no heat is lost. Okay, so they gave us the heat of the solution in kilojoules per mole. We need the heat of the solution. Oh, and by the way, we want to calculate the final temperature. This is what we're looking for. So we need the heat of the solution in just joules, right? So you take your 5 grams, you convert it to moles, you multiply by the heat of solution in kilojoules per mole, and you get that it is 55,600 joules. And it is negative, because see here, the negative here. So that is how much heat is released when sodium hydroxide is dissolved. So the heat that the water absorbed, here I forgot a 0, so let's just add that in there, is 55,600 joules. Okay, now here is the key point. When you are dissolving, you have to add the two masses together. So you have 1 liter of water, and the density of water is 1 gram per milliliter. Right, you have 1 liter, which 1 liter is 1,000 milliliters. So that's 1,000 grams, right? So the mass of the water is 1,000 grams. This is the water. And the mass of sodium hydroxide is 5 grams. You add them together, you get 1,005. So now we're going to use the heat of the solution, which is positive 55,600 joules. The mass of the solution, we're going to use CP of the water. We assume that the solution and the water have the same heat capacity. And then we just, for delta T, remember delta T is T final minus T initial. So we just plug that in, and then we solve for T final, and we get 33.2 degrees Celsius. It's always good to go back over these and see if you could get the same answer. So now here we're mixing 2 aqueous solutions. We have 50 milliliters of 0.1 molar and 50 milliliters of 0.1 molar of HCl and NaOH. And they're both at 22 degrees. They're added to a coffee cup calorimeter. The temperature of the mixture ends at 28.9. What is the approximate amount of heat produced by this reaction? assume no heat, this should be no, heat is lost and that the density of water is 1 gram per milliliter. So, Q of the reaction is equal to negative Q of the solution. The mass of your solution, you have 50 milliliters of each one, and we're assuming 1 gram per milliliter here. So that means we have 50 grams of each. So your mass is 100 grams. Your change in temperature, it ended at 28.9, it started at 22, so it's 6.9. And now you're just going to use Q of the reaction is negative heat of the solution, so you need a negative in there. The mass, Cp, times the change in temperature, and you get negative 2,900 joules. So this is exothermic. The last thing we need to talk about is how to calibrate a calorimeter. We won't do this a lot, but it is useful that you know that there is some error associated with your calorimeter. And the way you calibrate it is you have water in your calorimeter and you know the mass and the temperature of it. Then you heat water to a higher temperature and you know the mass and the temperature of that water. You pour it in and you could calculate what the amount of heat for the hot water should be and the amount of heat with the cold water should be, and they should be the same. If they are not the same, the difference in them is the error associated with your calorimeter. So let's break this apart. So here we're calibrating a calorimeter. We have 72.55 grams of water at 71.6. So this is going to be our hot water. This is our hot water. You add it to a calorimeter that had 58.85 grams of water at 22.4. So this would be our cold. You stir it, you wait for it to reach its final temperature, and the final temperature it reaches is 47.3. So let's calculate Q hot. We have the mass of our hot water, Cp, the change in temperature, it is negative 7,380. Does that make sense? The hot water is losing heat, so it should be negative. The cold water is gaining heat, so it should be positive. So you plug in the mass of the cold water, the Cp of the cold water, you change the temperature, and you get that. Okay? So then we're going to use this equation right here. Negative Q of the hot should equal Q of the cold plus this heat capacity of your calorimeter times your change in temperature. So we have our values right here. So we do 7,380. It's positive now because this is negative, right? A negative of a negative number becomes positive. Q of the cold is 6,130. This is what we're looking for. Our change in temperature is as such. You could calculate it and you get 50.2 joules per degree C is absorbed by the calorimeter. So now you know how much error you will have in this particular calorimeter. So here is a sample AP type question that deals with this. So let's pause kind of and read this here. A student performs an experiment to determine the enthalpy of combustion of 2-propanol. That's this right here. Which combusts an oxygen according to the equation above. The student heats a sample of water by burning some of the propanol that is in an alcohol burner. This is kind of like a lamp, okay? And the burner uses a wick, that's kind of what this is here, like a string, that draws the liquid up to the flame. You measure the mass before you started and the mass after, and that gives you the mass right here of 2-propanol that you combusted. Okay? Let's see what they want us to do. So in A, calculate the magnitude of the heat energy in kilojoules. So that's important. They want it in kilojoules. Absorbed by the water. So if it's absorbed by the water, it's going to be positive, right? Assume that the energy released from the combustion is completely transferred to the water. So there is no heat loss to your calorimeter. So you need the mass of the water that's being heated. You know Cp of the water. So here's your mass. Here's your C, and here's your delta T. Your delta T is your final temperature minus your initial. This is in joules, so you have to convert it to kilojoules. Based on the experimental data, if 1 mole of 2-propanol is combusted, how much heat in kilojoules is released. Report your answer to the correct number of significant digits. So this is the mass of our propanol. So let's convert that to moles because we want to know 1 mole, right? Then we take our answer from part A and we divide it by our moles, and that gives us, and it says you have 1 mole that you're combusting. So 1 mole times the heat for the reaction over how many moles we had. And that gives us 1,700 kilojoules is released. Okay, now in C, it says if a second experiment was done with the same amount of water, but it was found the alcohol was not pure, but contained some dissolved water. If the change in the mass of the lamp was still 0.55 grams, how would the temperature of the water in the beaker compare to the first? Well, the temperature would actually be lower. It would be less. Because in this 0.55 grams that you combusted, it is not all the alcohol. There might have been some water that evaporated or whatever. So if it's not all the alcohol, then you're not going to get all the heat from combusting that. So you'll have less heat produced, so the temperature will be less. Well, that is it for our reviewing of how to do calorimetry calculations.